Welcome to this explainer. Look, if you're tracking the bleeding edge of artificial intelligence, you know that for the last few years, the entire industry has basically been obsessed with one thing: fluent text generation. Getting AI to write beautifully, sound incredibly smart, and converse naturally. But sounding smart, that's no longer the actual frontier. We are right in the middle of a profound shift, moving away from just fluent generation and toward rigorous, verified discovery. And to really grasp how this works and why it matters, we're going to dive into a highly specific, honestly fascinating case study.
So, 95.7%. Imagine a system failing 95.7% of the time. Normally, you'd pull the plug, right? Well, recently DeepMind tested a mathematical reasoning system called AlphaProof Nexus against a collection of incredibly complex, open math problems, specifically ones related to the legendary mathematician Paul Erdős. The system failed on 95.7% of the problems it attempted. But this isn't a failure story, because that remaining 4.3%, that represents the successful resolution of 9 historical, decades-old open problems that human experts couldn't solve for half a century. And it pulled this off for just a few $100s in compute per problem. This is the central paradox we need to unpack today.
How exactly does a massive 95% failure rate translate into an industrial breakthrough?
To understand that, we have to look closely at the engine behind it all, something called the verified discovery loop. You see, to guarantee certainty, we have to completely step away from the old way of using AI. We can't rely on a language model writing persuasive but fundamentally unverifiable prose. Math has zero tolerance for persuasive nonsense. One hallucinated lemma, one hidden logic gap, and the entire proof is dead. So enter this verified loop. Notice the strict discipline here. The frontier model is treated purely as a generator. It explores, it mutates, it basically provides the raw cognitive energy to create candidate attempts. But step 3 is the unforgiving gate. Every single theorem and inference is translated into a machine-checkable formal validator, like the lean proof checker. The model can guess all it wants, but the final answer must survive that absolute machine judge before it ever becomes a verified deliverable. Think about the fundamental difference here. Normal generative AI is just trying to make an answer look right to a human reader. It's aiming for plausibility. Formal AI discovery forces the answer to survive an absolute judge. It either type checks and verifies, or it is immediately rejected. There is no probably good in this system. Which brings us to the most fascinating mechanism of this whole setup: how it harvests failure as fuel. What actually happens when the system gets a red light? When an AI attacks a half-century-old problem, its first few thousand attempts are going to fail. Now, conventional systems just toss those failures in the trash, but this architecture recycles them. It enters a tournament loop where the system treats failure as a gradient. A rejected proof might actually contain a near miss, or maybe a highly useful lemma. Or it could outline a really promising route, even if it ultimately hit a constraint violation at the end. By using a cheaper judge model to score which failure is, let's say, less wrong, the system takes the most promising failures and feeds them right back into the generator for the next cycle. In high-value discovery, cheap failures are perfectly acceptable, as long as you can learn from them.
But here's the catch, and it's an important one. DeepMind found that when they swapped out that core frontier model for smaller, cheaper models, the system produced exactly 0 solutions. Why is that? Well, to harvest the failure actually has to be structurally sound. A smaller model doesn't just make subtle mistakes, it often produces pure noise. Its errors lack the underlying structure needed for the verifier and the judge to extract any useful direction. You can't refine a near miss if the output is just incoherent. So while an external harness can massively amplify a capable model, it can't manufacture deep reasoning out of thin air.
So, zooming out a bit, this specific case points directly to a much broader architecture for reliable discovery. We can look at this through the lens of the energetic paradigm, or EP. EP treats AI reasoning precisely as cognitive energy flowing through strict constraints. AlphaProof Nexus shows us a really important fragment of the future in mathematics, but EP generalizes that verified loop into a full reasoning and discovery architecture. In this view, raw generation is just an energy source. It's unstable. For reliable discovery, that energy has to be routed, filtered, recycled, and put through hard verification gates before it can be trusted. And that architecture surrounds the core loop with these crucial layers. It starts with problem shaping, defining the exact constraints.
Then you have search routing and cost allocation to make sure the system doesn't blindly burn through compute. When it does fail, failure diagnosis figures out exactly why, and memory stores those useful partial steps we talked about. Finally, closure logic dictates when the system actually has enough hard evidence to stop searching. This provides the general discipline needed to turn unpredictable intelligence into dependable production.
Now, of course, this isn't magic. There are very real limits and hidden bottlenecks here. The biggest one? Formalization is incredibly expensive. You can't just throw a messy business problem at this system. Human experts have to translate it into a machine-checkable environment. This is elite knowledge engineering, not cheap data labeling, and it is shifting the entire financial reality of AI. In the old scaling story, your massive costs were all in pre-training and data. Now, the bottleneck shifts to inference, running millions of iterations, and formalization. If your search loop lacks the discipline of cost allocation and routing, your inference costs will just explode into a financial sinkhole without ever finding a solution.
So, why does all this matter if you aren't trying to solve historical math problems? Because this search economy is expanding.
This verified approach extends directly into messy, high-stakes domains where reliability is absolutely non-negotiable. Look at the bottom row here. In software, the validators become unit tests and static analysis. In chip design, generated candidates have to survive physical, thermal, and timing rules. In AI, drafting a legal contract is useless unless it passes contradiction checks, jurisdictional rules, and strict internal policy. In drug discovery, generated molecules have to clear simulation filters for toxicity and manufacturability. Across all these industries, the fundamental structure isn't AI writes an answer. It is AI generates candidates inside a verified search economy.
And this leads us to the new battlefield, building the control layer around the model.
The future of advanced AI is not only about building bigger, more capable models. It's about the stronger systems we build around them. Things like AlphaProof's Nexus aren't the end of human expertise. They represent a shift toward a new kind of expertise. We need professionals who know how to define the judge, encode those unforgiving constraints, extract useful failure memory, and manage the energy of AI discovery. The control layer itself is becoming the primary asset.
So I want to leave you with a central thought as we wrap up this explainer. As these advanced generative models enter your specific domain, whether that's law, engineering, finance, or medicine, ask yourself, do you merely have a raw energy source, or do you have the control layer required to turn that generation into reliable, accountable, verified discovery? Think about how your industry is going to manage this transition, because the era of verified discovery is already here. Thank you for joining us today.